Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences of IGNOU, and today I'll be discussing with you about minimum cost spanning tree, and specifically we'll be discussing about Kruskal's algorithm in this particular session. Well, this Kruskal's algorithm, and we will be discussing another algorithm called Prim's algorithm in the next session. Both these algorithms follow a greedy approach. Now, greedy approaches are basically used for solving optimization problems, which basically maximizes or minimizes the objective function, right? Which these objective functions are further put to certain constraints or conditions. So that becomes the optimization problem, where you will be solving the optimization problem with the constraints, some constraints which will be limiting the solutions, and the problem will be either to maximize the objective function or minimize the objective function. A greedy algorithm picks the best choice from the available choices at a particular moment to optimize a given objective. Well, if we are doing this Kruskal, like we are trying to find the minimum cost spanning tree. Now, obviously this problem is related to a graph, right? So the first thing let's try to define is how a graph is going to be represented when we are going to use this Kruskal's algorithm. Okay, so a graph technically is what? If I say a graph G, which consists of set of vertices V and set of edges. Okay, and interestingly, the set of edges is from the mapping V cross V, that is from one vertex to another vertex. So vertex, it can be maximum from, it can be from one particular vertex to all other vertex. That is the maximum number of edges which are possible in a typical graph. Further on, what we will be using will be a weighted graph, because we are trying to find the minimum cost spanning tree, right? So a weighted graph is represented. So we will be using weighted graph, and that weighted graph will be represented with the help of an adjacency matrix representation. Now, what is an adjacency matrix representation? We have already covered adjacency matrix representation in a previous session. However, let's take the example here. What we see is a graph which consists of 7 nodes, right? And there are a lot number of edges in this particular graph. So how this particular graph is representing this information? So A to A, there is no edge, there is no self edge, therefore the weight is 0. Okay, it is always like that. All the diagonal elements basically represents B to B or C to C, that kind of a situation, right? So this is going to be like there are no self edges, so the diagonal elements you can see are basically zeros. Now look into when we are looking at an edge A to B, right? So there is an edge from A to B. Okay, so there is an edge from A to B, and what is the weight of that particular edge? 2, right? This is 2 and this is 2. And this is once again from B to A also we have the same weight, right? So it is basically, you can see that the diagonal elements or the triangular elements are the same, all right? Similarly, A to C, the weight is 1, and here you can see that both the weights are 1. Okay, infinite basically represents, in this particular case, when there is no direct edge from a particular vertex to another vertex. For example, from vertex A to vertex D, there is no edge. That is why it is being represented as infinite. All right. So you can see that it is this particular matrix is having the similar elements on over here. So 4 is here, 4 is here. And now if we are referring to 4, D, A to that is this D is from B to D. So we are referring to this particular edge. So all the way you can refer to this 7, you can see that they are referring to typical edges, C to D, okay, or D to C, which are the same edges. All right. What is a minimum spanning tree? Well, a spanning tree basically is a tree of graph consisting all the vertices, and minimum spanning tree basically has the tree with the minimum weight. All right. So if I refer to this particular graph, all right, this complete graph over here, the minimum spanning tree is over here, which basically consists of minimum weight edges in this particular case. However, it is forming a tree. Not all minimum weight edges will be there. Only selected minimum edges will be there, so that this tree has the minimum weight. All right. So that is the objective. And as we stated, we will be using the greedy approach. All right. Then what are the properties of this minimum spanning tree or minimum cost spanning tree? It has V minus 1 edges only. The graph may have lot many edges. Okay. It can even have V cross V number of edges. But this minimum spanning tree has just the number of vertices minus 1, okay, because that is how a tree is. Suppose a tree consists of two vertices, it will have just one edge, so one less. If a tree consists of 3 vertices, then it will have just 2 edges, right? So that is what it is, okay. So that is why we have V minus 1 edges in the minimum spanning tree. Then MST does not have a cycle. Minimum spanning tree never has a cycle. If there is a cycle, the number of edges will be more, right? And in any case, trees do not, by definition, trees do not have a cycle, okay? So that is what it is. And MST may not be unique for a graph. We may get unique MST in several cases. However, there may be similar cost trees as far as MSTs are concerned. So there may be multiple minimum spanning trees in a graph, okay, it may not be a unique. However, we may be, our algorithm will find at least one of those minimum cost spanning tree, right? And that is what is the basic purpose of finding that particular thing. Now let us talk about the Kruskal's algorithm and how it works. Well, the Kruskal algorithm basically is a very interesting algorithm, a greedy algorithm. So, greedy approach is basically we have to greedily select the edges. Now, if we have to greedily select the edges, what is the first step we will do? We will sort the edges in a non-decreasing order of their weight. Non-decreasing order, why non-decreasing order? Because we want to first select the edge which has the minimum weight. All right. So that's how we are going to proceed. That is why we will first sort the edges, right? Then select the edge with minimum weight, okay? And then we will check, does it form a cycle of as far as any subgraph is concerned. So there may be multiple subgraphs as far as Kruskal's algorithm is concerned, and what we need to check whether there is a cycle being formed when we select a new edge into it. If no, select this edge for the graph and add it to the subgraph of MST. Okay. If it doesn't form a cycle, obviously it is still forming a tree. So let's add that particular thing into the MST. Otherwise, simply discard that particular edge because it is forming a cycle. Now, this particular step, this step 2, okay, this step 2 is repeated until we have selected V minus 1 edges, okay, or V minus 1 edges in the subgraph. Okay, so this graph is a minimum spanning tree of the graph G. All right. So this is how this whole thing works. All right. Okay. Now what is the algorithm for this? Well, the Kruskal algorithm takes 3 parameters, V, E and W. So what is E? The set of vertices of the graph. What is E? The set of edges which are there in the graph. And W is the matrix, right? Basically representing the adjacency matrix, which represents the weight of every edge, right? And we start with the set K, okay, which is a set of edges which has been selected for the minimum cost spanning tree in this Kruskal's algorithm. And we initialize it to null, right? That is how we are going to start, because no edge has been selected in the start. Okay. Now, what we will do for each vertex V, which is part of the set of vertices, make set of that particular vertex. That means every vertex will be assumed to be consisting of in a set. So, we will be creating, suppose there are n vertices, we will be creating n sets. Alright. Then we will be sorting the edges E in a non-decreasing order by weight. So, what we have done? We have done 2 things. Number 1, we have created a set of vertices, right? And how many sets we have created? As many as there are number of vertices. And in addition, we have sorted the edges in the non-decreasing order. Now, next step, what we will do for edge U to V, okay, which is a member of set of edges, okay. Now, this particular set of edges in non-decreasing order, right. So, from this sorted list, find set U which is not equals to set V. So, what is there? Now, any edge consists of 2 vertices. It basically joins 2 vertices. So, what we are checking in this particular step is that the starting point of the edge and the ending point of the edge, okay, those 2 points, are they falling in the same set or not? Okay, same set of vertices. So, we are creating set of vertices which we initially started when every individual vertex is a set. So, now we are just checking here that the U as well as V, okay, that is the starting edge, starting point of the starting vertex and ending vertex of the edge, are they falling in the same set or not? If they are not falling, right, they are not equals, right, then you add that particular vertex, because it is a greedy approach. We have selected the edge which has the least weight. So, simply add it into the set of edges, which is K, which forms the minimum cost spanning tree. So, keep on adding edges over there by doing the union, adding that particular edge into the K, okay. And just the union, just formalize this particular union, okay. Formalize this union U and V in the sense that U and V, which were different sets earlier, alright. U was in a different set and V was in a different set. Both those sets, this set of vertices, get combined. Alright. So, this is what is a very important step. I think you will understand it better when we do the example. Alright. But this is a very important step which will be combining the 2 sets of vertices which has now been put into this particular set of edges which forms the minimum cost spanning tree. And finally, when all this process is over, what we get in K is set of all edges which forms the minimum cost spanning tree. So that is what will be returned in this particular algorithm. So let us do an example of this particular situation. So what we are doing, typically working of Kruskal's algorithm, and we will be discussing it along with the algorithm which we have discussed right now. Okay. So this was our initial graph, right? So now this particular graph consists of 7 nodes, all right, and there are number of edges in this particular graph. 9 edges are there in this particular graph, all right. So what is our objective? Okay, objective is to find the minimum cost spanning tree. So let's run the Kruskal's algorithm. So what we start in the Kruskal's algorithm, we make the set K as null, right? So K right now is null, no edges there, right? So K is just a null set. For each vertex V, which is a member of set of vertex, make set V. So we make these sets. So what are these vertices? A, B, C, D, E, F and G. So we have made them as sets. Okay. So make set, we have made these sets. How many sets have been made? As the number of vertices. That's what I was saying, right? Then sort the edges in E in non-decreasing order of their weight. So the first edge which is having the least weight is AC. So it is appearing over here. Next is AB. Okay. AB comes here. Next is DG. So DG is here, right? Like that. Okay. So you can see that these edges are put in non-decreasing order. Alright, so we have got the edges into non-decreasing order. So these were the first 3 steps, technically the initialization step, where K has been set to null, it is a null set technically having no value, okay, and each vertex has been made as a set of vertex. So there are 8, as many vertices are there are as many, what we see is the number of sets which we have created. Okay. Now move to the first step. Okay. So for the edge UV which is member of E from the sorted list. So this is going to be this particular edge, the edge with the smallest weight, right? Because that is what we are picking up from the sorted list. So this is what is shown in the graph here. Okay. So AC, we have picked up AC. Okay, when we picked up AC, if find U and is not equals to find set V. So what is U in this particular case? A. What is V? C. Both A and C at the start were different sets, right? So these two were different sets at the start, alright. So when they are different set at the start, therefore, what we will do? We will add this particular edge into K, right? So AC has been put over here and union of U into V. So this is what is showing the union of set A consisted of A, the set for C consisted of only C. So these two have been put into one set, that's why it has been removed from here. This is no longer there. And what we have got is AC as a new union. So our sets now are AC, B, D, E, F, G. These are all separate sets. Alright. And this particular one has become part of the minimum spanning tree. Alright, so this is the first step. Okay, then we move to the next. What happens? Okay, we go slightly back, and what we see here is the next one is A to B. So when we do A to it is A to B. So this is the edge which has a weight of 2. So what we check? A is part of AC. B is a separate set, right? So now AB is the right candidate to be selected, all right? So once AB has been, so this particular thing has been checked, all right? A was different set, B was different set, all right? It is during the find set they were found to be of different set. Therefore, we will add edge AB also in the set of K as per this particular instruction. So, we have added this particular thing, all right. Now, perform the union of the sets containing U and union of set containing V. The set containing U was actually AC, all right. This was the set AC, which contained A, and B was contained in B. So, we took the union of A, C and B, and the new set now which has been generated after the union is ACB. All right. So, this becomes the new set, and now B is no longer the extra set. So, both of these B and C have been eliminated. So, now we are left with one set ACB, another set D, another set E, F and G. Let's go to the, so we have already selected these two, okay. So, now let us take the third edge, DE. So, this is the edge now we are considering, all right. D is a separate set and G is a separate set, okay. D as well as G, both are separate sets, okay. We have found the sets of D as well as found the set of G. They are not the same, therefore, add this. So, we want to add the edge DG into this particular graph, all right. So, we need to add it, okay, and thereafter we will need to perform union of D as well as G. So, that will become DG, all right. So, we have added this particular edge, okay. Now, this is a separate tree altogether. There are no cycles, right. There are no cycles. Cycles are being determined by this particular statement, okay. So, you are getting this particular node as a separate node, okay, and DG now has become one particular set, all right. Now, what is next? So, we have added DG, now we need to add BE, okay. Now, B and E, once again B is here in this particular set, E is here. So, what we need to do? We need to merge these two sets and get another set ACBE, as well as we will get this particular edge BE over here, all right. So, now edge BE has come in to the minimum cost spanning tree, right, and like that DG has been made another set, all right. What about BD next? Okay. Now, when we see BD, all right, so we have added till BD. Now, in BD, D is part of a separate set, okay, this set, and B is part of this particular set, separate sets. Once again, BD will be added to minimum cost spanning tree, all right. So, we will add it to the minimum cost spanning tree, and the next edge which will be added over here is going to be BE, right. So, we are already added DG, now it is going to be BE has already been added, okay, and BD will now be added thereafter. So, BD has been added, BE has been added, DG has been added, like that, and now our set has become ACBEDG. So, this has become a good big set, all right. So, you can see only F is another node which is left, okay. At this point of time, BD has been added. So, let us look into the next one. It is ED. The ED has a node weight of 5, but E is already part of this particular set, so is D, okay. D is also part of this particular set. Therefore, this particular condition is false. They are equals. They are in the same set, All right. Therefore, the new node, that is the new edge, that is ED, is not going to be added. All right. ED will be simply ignored. Okay. Then the final, this CF edge will be taken up. Okay. Now, this CF edge is basically this particular edge. F is not part of this particular, F is separate. So, we will be creating this particular node. Okay. And ED was not needed. Okay. And CF will be added. ED, because ED was falling in the same set. Now, CF will be added. All right. So, CF has been added, and our, if we see, we had 5, 6, we had 7 nodes, we have already 6 edges. We can simply stop this particular algorithm. Now, we have obtained the minimum cost spanning tree. So, we have shown that all these 3 now can simply be discarded, and we will simply return k, right. So, k consists of this and these edges only, and that forms, which are shown in this particular situation. So, that is how this particular algorithm works, and it is going to give the overall minimum cost spanning tree. All right. So, this is our minimum cost spanning tree, and the weight of that minimum cost spanning tree, you can simply sum up all the edges. So, if you sum up all the edges, you will get a weight of 18. Now, what is the complexity of Kruskal's algorithm? Well, when you looked into the algorithm, when first three lines were the initialization, right? So, the first initial k was just taking order 1 time, line 2, that makes set took order v time only, as many vertices are there. Line 3 takes order e log e time, because that is what is the efficiency of sorting. So, we are actually doing the sorting of e edges. So, that is going to take e log e times, n log n, that is what is the efficiency of sorting algorithm, right. And the second loop for find set and union, which we were doing towards the end, like we were repeating this particular operation, whether the edge is to be added or not, take order log e times, because it is sorted. Okay. Thus, the total time taken by that particular step is going to be e log e only, right. So, e times that particular the loop will be repeated, and log e is the number of times it is going to be checked. All right. Then, adding all these times all together, what we get, and if we assume the worst case, the number of edges are v cross v, that is v square, which is very, very high. That is, from every node there is an edge from any other node, including the self edge also. Then we get an order of e log v square plus e log v square, which once again can be converted into an order e log v. So, e log v is the actual time when we are dealing with, when we are using the Kruskal's algorithm, and specifically we are dealing with the Kruskal algorithm with adjacency matrix representation. Now, let us summarize what we have discussed in this particular session today. A minimum spanning tree is a tree of minimum weight that connects all the vertices of a graph. Kruskal's algorithm keeps adding the smallest possible edge that does not make a cycle and create the minimum cost spanning tree. It selects the smallest new edge which is not forming a cycle and adds it to the tree every time. Thus, it is a greedy algorithm, and the time complexity of this algorithm is order e log v. With this, we end this particular session. Thanks for being with us.